So, hello everyone, welcome to OneClass. My name is Shanjida, and today I'll be going over some commonly asked chemistry questions, both at the high school / university and college levels. And so, I'm currently a second year human biology student studying at UFT. And lastly, if anyone needs additional schoolwork help or needs tutoring, you guys could check out the description box below. And with that being said, let's get started. And so the first question for today says, is xenon or XEF4 polar or non-polar? Explain your answer. So we're supposed to find if xenon tetrafluoride oops, polar or non-polar. Okay. And so basically what we need to do is let's address the symmetry of the dipole moments, right? So it's very important to address the dipole moments when we're talking about polar or non-polar bonds. And so we need to see if the dipole moments are basically in symmetry due to the electronegativity difference of the atoms that will make the molecule polar or non-polar. And if it's symmetry, then we know that the molecule will be non-polar, and if it's asymmetric, the molecule will become polar. And so the Lewis structure can give us an insight into the polarity of the molecule, right? So the Lewis structure for xenon tetrafluoride is C. You have 4 fluorine atoms, right? And if you look at our periodic table here, xenon is down here, and it's a noble gas, right? And you see it has 54 electrons. And so in this case, they're saying that it has 2 lone pairs. And you know that fluorine would have, fluorine in this case is group 7. And so you can say that it would have, since it's bonding with 1, right? You have an excess, or the remaining electrons would be in 3 lone pairs. That goes for all the fluorines. I don't think xenon would have that. So, anyways, so okay, so this would be your structure. And so as you can see, there are 4 xenon and fluorine bonds and 2 lone pairs present in the central atom. Okay, and so the 4 xenon and fluorine bonds will basically eventually cancel out because of the dipole moments present and the symmetric configuration. So let's look at our electronegativity chart. And we know that fluorine is the most electronegative. Okay, and xenon is not in the chart because it's a noble gas. So what we can say is that our fluorine is more electronegative. And so in this case, I don't think electronegativity will play because your xenon does not really have an electronegativity difference. And so you can tell by the if we represent vectors here, right, it would basically get cancelled out, right, because opposites, and right, so your vectors would cancel out for your dipoles, and so you would basically have a net net dipole moment of 0. And so you can say that therefore your molecule of xenon tetrafluoride is nonpolar. Okay. And this is what they have. So the solution here is correct. Okay, so our next question says, the aqueous designation listed after a solute indicates the process of hydration. Using potassium bromide and ethanol as your examples, explain the process of hydration for soluble ionic compounds and for soluble covalent compounds. Okay, so in this case, let's figure out which one is our soluble in ionic compound, and you can see that potassium bromide is our soluble ionic compound. So KBr. This is our soluble ionic compound, right? Okay, and so when soluble salts dissolve in water, right, the ions in the solid separate and disperse uniformly throughout the solution. So when you have a salt that dissolves in water, it would dissociate into their ions. And this process represents a physical change known as dissociation. So example, we have, let's say potassium chloride. Example. We have potassium chloride as an example of soluble salt. So it's added with water. So let's say H2O, right? This will, the positive hydrogen end of the polar water molecule is attracted to the negative chloride ions. So you have the LO, right? So what you would have, so the polar water molecule, the positive hydrogen would be attracted to the chloride ion, so you would have HCl. Okay, and then to the negative chloride ions, and the negative oxygen ends will be attracted to the potassium. So you have KO. And so you would have something like this, and so the water molecule surrounded by the individual your potassium chloride ions, reducing the strong forces that bind the ions together and letting them move off into a solution as solvated ions. Right, so then you would basically have these floating around as your ions. So you would basically have your chloride ions and your potassium. Okay. So yeah, in this case, for let's say, so for ethanol, it involves the concept of soluble inorganic compounds. So C2H5OH, this is for soluble organic compound. And so basically, the polarity of organic molecules is determined by the presence of polar bonds due to the electronegative atoms. Example, nitrogen, oxygen, fluorine. In polar functional groups such as amines, you're in an H2, so the polarity. So this is for organic compounds, is determined by the electronegativity. It's determined by the electronegativity of the atoms. Okay. And also in polar functional groups, these are such as your amines and alcohols. Okay. And so overall polarity is a balance of the nonpolar parts and the polar parts, and it can be convenient to basically break a molecule into its polar and nonpolar parts. And so a larger nonpolar organic hydrocarbon part will tend to make it less soluble in polar solvents, right? So we can write this down. So a large nonpolar molecule large nonpolar or hydrocarbon. Hydrocarbon will not dissolve or will not be soluble. Will not be soluble in polar solvent. While more polar part or polar hydrocarbons will be more water soluble. Right, so this makes sense because of the partial charges in the molecule, and so will be more water soluble and in polar solvents, right? But not in non-polar solvents. Non-polar solvent. And so this is basically our answer. And we can see that added to water, negative, and so the polarity is determined by the presence of polar bonds due to the electronegative atoms, right? Meaning less soluble in polar solvents, and yeah, so this and the solution is correct. Because our next question says, what mass of sodium chromate is required to precipitate all of the silver ions from 75 milliliters of 0.1 molar solution of silver nitrate? Yeah. Okay, so what we need to do is first set up the chemical equation for the reaction. And this is a double displacement reaction because we're using two reactants. And so let's write this down. So the first part, you need to come up with a chemical equation. So we have Na2 4 plus AgNO3. This is a double displacement, so you would have NO3 plus AgCr. Right? And so you can see this equation is not balanced yet. We have two sodium on this end, so we need two sodiums on this end. And so in this case, since we have two sodiums, that means we also have two nitrates, and so we just put a 2 here, and we can put a 2 down here. Okay, and so now this is balanced. Okay, so now this is balanced. And so now, so this is an important part of solving this problem because we will be using stoichiometry. And so the problem wants us to get the mass of sodium chromate needed to precipitate all the silver ions present in silver nitrate. And so this means that all the moles present in silver nitrate will be consumed by the reaction. And so hence the number of moles of sodium chromate must be equal to silver nitrate because we are basically consuming all, so you can basically say since we're consuming all of the silver nitrate compound, you can say they will be equal. And so given the volume, right, of the concentration, which is 75.0 ml, so we can find the number of moles from concentration. If you guys just write the second step to find number of moles. So the reaction for moles was it was concentration. So original equation was concentration is equal to moles over volume, right? And so you can rearrange this equation to solve for n. So what we need to do is just multiply by v and get n. You have c times n. C is your concentration. So n. Okay. So what we need to do is convert 75 milliliters to liters. So we have to divide 75 by 1,000, and we can do this. So let's just first write the concentration, which is 0.100. Okay. Multiply by 75.0 ml times conversion factor, which is 1 liter over 1,000 milliliters. Right? And so what you have, once you do math here, you would get 0.0075 moles of of silver nitrate. Okay. So we just found our moles. So now through stoichiometry, the molar ratio of what's number 3. So through stoichiometry, the molar ratio of sodium chromate to silver nitrate um, is, you guys could see, it's 1 to 2, right? And so hence the number of moles of, so the number of moles of sodium chromate needed is, so you just multiply the moles that you got for silver nitrate and you multiply that by 2. Since the molar ratio is 1 to 2, it would be the way you would write it, or sorry, you would divide that by 2. So you would have 0.0075 moles of silver nitrate multiply this with 1 mole of Na2C4 over 2 moles of AgN. And so this is equal, we just divide the moles by 2, and you get 0.00375 moles of Na2Cr4. Okay, so we just found the moles for sodium chromate. And so what we need to do before we can determine the mass of sodium chromate, we need to find the molar mass, right? Since to get mass, we know that molar mass is equal to grams to mass over moles. We have our moles. So the next step, which is we don't really need any information to find molar mass, we just need to use a periodic table. We just find, so number 4, find molar mass. So yeah. Okay. Do that. So let's break this to the individual parts. So we have molar mass of 2 sodium atoms, and then we have the molar mass of chromium and the molar mass of 4 oxygen atoms, right? So the molar mass of sodium is 22.99. So I'll just say, so you have to multiply this by 2, 22.99 grams per mole. That's chromium. Chromium is right here, and it has a molar mass of 51.9. 51.99. And we have 4 oxygen, so we multiply that with 4, and the molar mass of oxygen here is 16.02. We have 16.00 per millimole. And once you do the math here, you would get 161.972 grams per mole. Okay, so the molar mass of sodium chromate is 161.972 grams per mole. Okay. So now, as you can see, we found our mass. We found our molar mass and the number of moles. And so the last step, we can find the mass. Okay. So step 5, find the mass. So since we know that molar mass is equal to grams per mole, or actually is mass over mole, we can rearrange this equation to find m, our mass. So we just multiply both sides by n. And what you have, you basically get m is equal to n times m, your molar mass. And you get, so you would have, so the number of moles is 0.00375 moles. And you multiply this with your molar mass, which is 161.972. Right, you can see your moles get cancelled out. And so you have, your answer is 0.60. So we basically found the mass of sodium chromate needed to precipitate all of the silver ions is 0.607 grams. So this is the answer. And let's go the answers. Okay, the next question says how to convert grams to moles. Okay, to convert grams to moles, what you need is, so basically, there's a measurement used to determine the amount of substance that you need. So the mole quantity was derived in comparison with the Avogadro's number, which is 6.02 times 10 to the power 23. And therefore, 1 mole of any substance is exactly 6.02 times 10 to the power 23 particles. And in converting grams to moles, we simply determine the molar mass of a given substance. And we know that the molar mass is grams per moles. And to basically, so to go to convert this to moles, we just have to we basically have to move everything that is attached to moles to the other side. And what we have, so let's say moles to the other side first. We have moles. Okay. Then you would divide both sides of M are your molar mass, and you would get moles is equal to grams. Okay, that's how you get moles. And then the molar mass of a substance can be calculated by adding up the individual molar masses of each element present in the substance. Right? So let's say, for example, we have, so for example, let's say, let us convert 5 grams of water of water H2O moles, right? So now first we need to calculate the molar mass of hydrogen. So the first step to calculate. So calculate molar mass. Right? So break this down into their individual atom molar masses. So we have molar mass of H2 plus the molar mass of oxygen. Right? And so the molar mass of hydrogen is given in your periodic table right here. So this, since we have 2, we multiply this by 2 to 1.01 grams per mole. You add this with the molar mass of oxygen, and it is right here, so it is 16. So we plus this with, add this with 16.00 grams per mole. And so what you have is 2.02 grams per mole. Add this with 16.00 mole. And when you add these two numbers together, you would get 18.02 grams per. So the molar mass of water is 18.02 grams. Now you convert grams moles, right, from our equation. So we know that from our equation, we know that moles is equal to grams over molar mass. So we know that we said that let convert 5 grams of water to moles. We have 5 grams, and we have the molar mass. Molar mass is 18.2. Grams per mole. Okay. And so what you have is, we divide these two numbers, you get 0.28 moles of water. And so therefore, there are 0.28 moles of water or there are moles in 5.0 grams of water. So this was just an example, but this is how you convert grams to moles. Yeah, so we just use this example. So the solution is that. Next question says, what is the molecular weight of sodium hydroxide? And so the molecular weight is also known as the molar mass, and it could be calculated by the same way how we just calculated the rest of our compounds' molar masses. So the molar mass of sodium hydroxide, right? So you would want to first break those down into their individual elements molar masses. In this case, we have 3 elements that is making up sodium hydroxide. So you do molar mass of sodium plus your molar mass of oxygen plus the molar mass of hydrogen. And so let's go back to our periodic table. The molar mass of sodium is 22.99. So we write 22.99 grams per mole. And you add this with the molar mass of oxygen. Right here, it's a 16. We have 16.00 grams per mole. And lastly, we have hydrogen. And for hydrogen, this is right here, which is 1.01. So add 1. And so when you add these 3 numbers together, what you would have is you would have 40.0 grams per mole. And so the molar mass of sodium hydroxide is 40 grams per mole. And so the solution here is correct. Okay, so our next question says 12 grams of acidic acid and the molar masses given are dissolved in 188 grams of water, and the density of the whole solution is 1.12 grams per milliliter. So this question is divided into 3 parts. And so A says, what is the weight percentage concentration of the solution? Okay. The weight to weight percentage. So to find the weight to weight percentage, let's write A. Weight to weight percentage, right, of the whole solution here. So to find this is, so the weight to weight, so you guys could probably say that since we're talking about weight, we need to include mass, and to do that, we need to find the mass of the solute and the whole mass of the solution times that by 100. So you say mass of your solute for the mass of your solution. And you multiply this by. And so the mass of the solute here is acidic acid, and it's given by 12 grams, so we can substitute that. So you write 12 grams. And the mass of the solution, as you can see, it's 188 for water, and so the whole solution is, since the solution is containing water and acidic acid, so you would have to add the 2 masses together to get the mass of your whole solution. So in this case, it would be 12 plus 188. And so we have 12 over 200 multiplied by. Okay, and so what you would have is you would basically have and if you do the math here, what you would get is 6%. Okay, so your weight to weight percentage for the whole solution is 6.6%. Okay. To weight percentage. Okay, and so now for B, what we have is what is the molarity of this solution? And so molarity is basically the ratio of the number of moles, which is equal to the mass of solute divided by the molar mass of the solute, and the volume, and the ratio between the number of moles and the volume of the solution in liter. So to find the molarity, we need to find the number of moles and the volume. So therefore, we can basically say that let's first determine the number of volume, or the volume of the solution. So recall that we can find volume from our density equation, where density is equal to mass over volume. So volume, to rearrange this equation, we have volume is equal to, so we have the mass of our whole solution, which is 200 grams. So we can just write 200 grams, and our density is given, which is 1.12 grams. Okay, you can see your grams get cancelled out, and what you're left with is, what you get is 178. Oops, you get is 178.6 milliliters. And since this is in milliliters and we need it in liters to find concentration, you have to divide this 1,000 milliliters. And so what you have is, and let me write this way. So you basically write 1 liter, right, divided by milliliters. And this is equal to 0.1786 liters. So now we found our volume, and so the next would be to find the molarity, right? Since we can find the number of moles let's find the number of moles. And so we call that, to find the number of moles, we require molar mass and mass. And so for this, we would want to find the molarity, or we would use the molar mass of acetic acid and the mass of acetic acid. Since we're saying the mole of the solution is equal to the mole of their acetic acid, because it's completely dissolved in water. So we can say that the moles of acetic acid, so HC2 H3O2 is equals to the mole of the solution. So let's find the moles of acetic acid, and recall that molar mass is equal to your mass over moles. So to find moles, you can rearrange this equation. So we have moles is equal to mass over molar mass. So we know the mass of our acetic acid, which is 12 grams, over our molar mass, which is 60.0 grams per mole. And once you do the math here, what is 12? I guess it's 12. Okay. Is your point. Okay. Now, since we found our moles, we can now find molarity, where molarity is the formula for molarity. Formula for molarity is N over V, so your moles over your volume, and so we can just plug this in. 0.2 moles over volume, which was 0.1786 liters. Okay, and so the answer here would get 1.12 molars. Okay, so this is the answer for the molarity. And lastly, what we need to find for C, which was what is the molality of the solution? So molality is basically the ratio between the number of moles of the with the mass of the solution in kilograms. So molality, OM, the ratio is N of solute over the kilograms of solvent. And what we can say, we can basically substitute 0.2 for our of our kilograms of solvent, and we know the moles, which is 0.2, so you just put 0.2 moles over your 0. Over the mass of kilograms, mass of the solution, which is also 0. And so this would equal to 1 molar. Okay, and so the molality of the solution is 1. Okay, and so this is how you do this question. You see, we have 1, we have 1, 2, and we got 0. We got 6%, right? Yeah, so the solution here is correct. And next question says, what is the atomic mass of aluminum? Okay, so atomic mass of aluminum. So to find the atomic mass of aluminum, this is actually given in your periodic table. However, we can find this by saying that this is equal to the number of protons plus the number of neutrons of this element. So we know aluminum is in group 2. If you look at our periodic table, or sorry, in group 3, right? It has an atomic number of 13, so the number of protons is also equal to that. And in most cases, your number of neutrons will be equal to the number of protons, so we can say this is 13. So this, therefore, you add these two, you get 26. However, it is stated here that your atomic mass or your molar mass is 26.98 AMU, so this 26. To be more accurate, you have 26.98 of aluminum. Okay. And so this is one way to find atomic mass. Okay, but it's usually it's given in your periodic table. Okay, so this question says, which compound contains both ionic and covalent bonds? And so what we can say here that an ionic bond is an electrostatic force that holds ions together, an ionic compound. So, so bond is where it's formed by a metal and non-metal. Metal and non-metal. And so this is where and whereas your covalent bond is formed when there's two non-metals share their electrons in the bond. Okay. And so typically ionic bonds are found between a metal and non-metal, and covalent bonds are formed between two non-metals that we just said here. And so with this in mind, both B and D have a metal and more than one non-metal. You can say B and D, right? They have more than one non-metal. So non-metal in this case is carbon. For D is carbon and nitrogen, and for B is two chlorine ions. And so so this is because your cyanide is a polyatomic ion with a negative charge is carried by the carbon atom. And so we can basically show the compounds here, draw out the compounds. So we have A, we have glucose, we have our ion iodide. So I would put all the lone pairs. This is your negative ion. For B, draw out B. You have your chlorine, which is negative. Then you have your calcium, charge of +2, and your other chlorine atom, which is negative. Okay. And then you have C, which is methyl bromide. Yeah, so no, not methyl bromide, but it's like carbon group attached to two bromine atoms. So you have, I'll draw this out by carbon, and you have a hydrogen here, a hydrogen here, and you have bromine. So this is going to be a negative ion. That won't be negative in this case because it's bonded. So you have, and it has lone pairs. Okay. And lastly, our last compound is sodium cyanide. And to this, so we have Na plus, and you have your cyanide, which is a triple bond. You have C, triple bonded with nitrogen has two lone pairs, and this is your negative. Okay. So these are the 4 compounds that we have. And so the answer here, right, is correct. So okay, so our next question says, what is the name of HBrO4 acid? So H. So this is, as they said, this is an acid. We can say that this is an acid because there's an hydrogen in front of the compound, right? So that means that it has an additional hydrogen. And so the name of this is perbromic acid. So bromic comes from the BrO4, and per is from the hydrogen. Per. So this is correct. Okay, so basically that was the end of our session. If you like this Q&A, please subscribe to the OneClass channel, like, share, comment this video, and if anyone needs one-on-one tutoring sessions or has your own personal questions related to any of this topic, you guys could check out the description box below and follow the links to ask your questions. And other than that, I am Shanjida, and I hope to see you guys soon. Bye-bye.